I guess I started recording because it's the start of class. Although, hey Emma. Ooh, we got more. So what do we do today? I'm just going to lecture for a little bit and then go over kind of like, I didn't bring any molecular models, but we're just going to do like Lewis structure practice. Everything is non-graded. So it's just kind of an activity, of sorts. A little bit better than bringing coloring books, like we did in grade school before Thanksgiving, but if you want to color, that's fine too. Or you can make origami. I've ruined your circle. I don't know what you're trying to summon. You've summoned him. You've summoned the chemistry gods with their periodic table t-shirts and their face masks. All right, so where we left off, we're talking about, actually, does anybody have any questions or anything before we start? Okay, we left off, we're talking about the SCPR, and you like green, you said, right? I can stick with green. So you can combine this with Lewis theory. So predict the geometry and bond angles of PCl3. So phosphorus has 5 electrons plus 3 times 7 for chlorine, and that is 26 electrons. So phosphorus in this, I guess I already know the answer, but phosphorus put in the center with chlorines. So 6 electrons, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is, so the geometry, well, the electronic geometry is tetrahedral because there's 4 things, but 4 things, 3 bonding and 1 non-bonding. This is going to be pyramidal, specifically trigonal pyramidal. And that means the bond angles here, they're going to be slightly less than 109.5. So that angle, because of this region of negative charge, it's going to push down those chlorines a little bit, but it's going to be about 109.5 degrees. That's the angle on a tetrahedron. Do you need me to explain this more? Do you need more pictures, or are you guys good with that? I can show you the chart.
Should be with both angles.
I'm sorry, Summer, can you say one more time, please?
Should you also with the other 2 chlorines that their angle would be less than 109?
They're all going to be the same.
Okay.
Yeah.
Is that a triangle?
Here, it was 11. It won't be, it'll on the bottom. Well, on the bottom it should be, but it's not a tetrahedron. It's this line right here.
Okay.
It's the bond angles, like, and you can see here in the chart, it tells you it's gonna be a little less than 109.5. So, and of course you have this chart, when you're taking the tests. Okay. And ICl4 minus. So iodine and chlorine, they're both halogens. So it's 5 times 7 plus 1, because so 5, 1 iodine, 4 chlorine, so 7 halogens times 5, and then plus 1 because of the minus 1. So that's 36 electrons. So iodine in the center with the chlorines around. We placed 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So this is going to be, well, the geometry here is going to be square planar because of 8 things. I'm sorry, I can't octahedron. 6 things, 2 non-bonding, 4 bonding. That's going to be square planar, and the bond angles, they're all going to be 90 degrees. So, and I'll show, oop, switch to me. So 6 things, 4 bonding, 2 non-bonding, that's going to be square planar, and everything is perpendicular. So, questions with this one?
Which one is water?
It's bent. It's going to be right here. Tetrahedral bent. Okay, other questions? So sketch methanol and talk about the geometry of each interior atom. So it's already kind of listed the structure. It's giving you a hint. So this is just right ahead the structure. If you count the number of electrons, carbon has 4 plus 4 hydrogens plus 6 times 1 for oxygen, and that's 14 electrons. So each line we've placed 2, 4, 6, 8, 10, 12, 14. So that's all the electrons are placed. So if you look at this atomic center, the carbon, it's going to be tetrahedral because it's got 4 things and they're all bonding. If you look at this end of the molecule, at the actually, it's just look at the oxygen. If you look at the oxygen, still looks like. If you look at the oxygen, it's going to be bent because it has 2 bonding groups and 2 lone pairs. Again, I'm getting this from the chart. If you don't have to memorize a chart, but 4 things, all bonding, that's tetrahedral. 4 things, 2 bonding, 2 non-bonding, that's bent. And that's important because pretty soon we'll talk about polarity. And because this part of the molecule is bent, it actually means the molecule is polar, which we'll talk about soon.
And water's
polar. So let's see if you're following. What is the shape of ammonia? I've given you the abbreviated chart there. TD is tetrahedral.
Wait, you tell me what the electron groups are again? Like, what do you capture electron? No, or an electron group.
A bonding group or a lone pair?
Oh, it's either one of them.
Yeah, it's either bonding or it's not. It's like what do students in the class? They're either in the class or they're not, right? So it's bonding or it's not.
And there's 3 of us.
Well, 5 if you count the zoomers.
Well,
They're the electrons on
that's
top.
all you can do is just just count the amount of pairs and then count the amount of lone or bonding and then
Yeah.
and then count the amount of
Yep, that's it.
That's it.
Yeah.
The whole. Okay.
Yep, that's how you do it. So what do you think about ammonia? What do you think? Is the geometry linear? Is it bent? Is it pyramidal?
Good middle.
Yep, everyone's going an email on Zoom. Yes, it's pyramidal. That is right
We're so smart.
Yeah.
for ammonia. You are so smart.
A degree already.
I'd be fine with it, but how about ozone? Now, and there's a structure, the Lewis structure for ozone right there. How many think it's linear? How many think it's bent? How many think it's pyramidal? I think it's tetrahedral. So how many groups are there? For this one here, there are 3 groups, 2 bonding, 1 lone pair. So it doesn't matter if it's double bonded or triple bonded or single bonded. It just matters if it's bonded.
Can we observe this under a microscope? Electron microscope?
Electron microscope, you can't see atoms using light because the atoms are about 1,000 times smaller than a wavelength of light.
Okay.
So you can see it using either AFM or STM atomic force microscopy or scanning tunneling microscopy. Here, you'd more likely see it scanning tunneling, and you'd have to put it on like a metal surface. So you'd have to fizzy or I guess you'd have to fizzy absorb it to a surface, and then look at it with an STM.
So we have observed,
What?
we have observed it
Not necessarily for ozone, but we've observed these bond angles.
for other.
Yeah.
Because I remember, I think IBM, like a video, like made a video of like atoms.
Oh yeah, yeah, they did that. Yep, IBM did that. They moved atoms up and down. Okay. So, other questions?
Recall what the number.
Yeah. Yeah, it doesn't matter if it's single, double, triple bonded, or even quadruply bonded. It's just if it's bonding or if it's not bonding. Lone pairs are non-bonding. Everything else is bonding. Okay.
So that's the main need of the rest of the.
Yeah, and like, I mean, that's, yeah, at least as far as the geometries. So. Other questions, Dan?
You know, the library resource in Kia, the other science building, they have models, the golden models.
Okay, Ikalia, yeah, I guess I could have brought them. I didn't know how many people were gonna come, and I didn't want to, well, I guess probably being lazy, I didn't want to haul them over. You can go grab them. Yeah, I'm kidding. I mean, you can do it without models.
Yeah.
I thought about bringing them in. I was like, students can learn how to do it without models. It's the activity. Okay, so remember we talked about like blanket hogs and with hydrochloric acid HCl that the electrons, the cloud, it like, okay, this would be even Steven if as far as the bonding electron cloud is concerned, but because chlorine is more electronegative, it can draw electron density to itself. So that means that the real electron cloud more looks like that. At least the one where it's shared, the electron can be in many different places at once, and it spends more time around chlorine than it does around hydrogen. And because of that, you have a slight buildup of a negative charge on the chlorine atom, and then that leaves electron poor hydrogen gets a positive charge. And then this whole molecule we call it a polar molecule because there's a separation of charges. So you have a negative end and a positive end. The partial, this equates to less than 1.6 times 10 to the minus 19 coulombs. That's such charge of an electron or proton, positive proton, negative electron. So it's a partial charge, partial being less than the charge of an electron, and the two ends of the molecule have different charges. So this whole molecule becomes, we call polar. So now here's another polar bond with carbon dioxide. So carbon dioxide, oxygen is pulling electron density towards itself, but the other oxygen is also pulling electron density for themselves to itself. And because of this, though, because it's linear, the geometry of this is linear. The geometry for this one is linear as well. That's the only option for two atoms, but there's not another one here to counterbalance it. So here you have two vectors, two drawing forces, and the forces cancel each other out. Have you ever studied vector addition or component vector addition? You've never studied that. So a lot of this is in physics. So I have gravity, if you can model it, my center of gravity being pushed down. So then the floor is pushing back at an equal opposite force. So the forces cancel, and I don't go anywhere. Right, gravity is canceled by the normal force. Normal just means perpendicular, so the force is perpendicular to the surface. And because of that, I'm not moving. And If you take away the floor, what happens? I fall until, until I reach the center of the earth and or something stops me. And then the force is canceled. What's that?
It's like tug of war, basically.
Yeah, and they cancel. And you didn't watch whatever Squid Games yet, have you?
Nope. Why?
They have tug of
Oh,
war.
wait. I see what
They have
you're
tug of war in there. Have you guys seen Squid Games?
Yeah, I can't say, like, I can't think of like anymore.
Oh, that's the other thing. We're gonna play red light, green light.
saying. Okay.
No, I'm just kidding.
I'm gonna get those molder.
Yeah. So just plain old forces, I'm trying to show here that they, like up and down or left and right, they can cancel if they're equal opposite. So now water has, so here is water's, I can redo this. So with water, it's also a polar bond, and you get a vector going in this direction. You have another vector going in this direction. And what happens is, so you have this vector plus this vector. And what happens is that you can write these vectors as these components. So like this and like this. So these components, they cancel each other out, but the highlighted in pink here, they actually add. And then overall, you get an overall electron flow in one direction. And because of that, you get a negative end of the molecule here and a positive end of the molecule there. So water is also polar.
Do I get bond itself easy?
In between the molecules, it can't. Are you talking about intermolecular or intra, within the molecule or between molecules?
Between them.
Yeah, I can bond pretty easily. Bonds very well, actually, which you'll learn next semester. Mwah. So, but the idea here, though, also, and I know we're taking a bunch of random math facts. These you can write vectors as a series of components, and the proof for, I mean, I'm trying to talk about the overall polarity, and then because of that, since the components along the, as written, the x-axis, they cancel, and then they add along the y-axis there, and you end up having a negative end of the molecule and a positive end of the molecule. Again, partial because it's less than the charge of an electron. So how do you figure out shape and polarity? Draw the Lewis structure, determine if there's polar bonds. It's really easy to figure out if it's a polar bond. If it's not the same atom, it's a polar bond. If it's a different atom, it's a non-polar bond. And determine if the polar bonds together form a dipole moment. So it has to do with symmetry. So if you look at two different molecules, so linear, if they're the same atom, it's non-polar. So if you look at carbon dioxide, already mentioned, carbon dioxide is the same atom, they pull and they cancel each other, it's non-polar. But for something like cyanide, so cyanide, it's carbon with a nitrogen and a hydrogen, central carbon with a hydrogen and nitrogen. They're different atoms. Therefore, there's a break in symmetry. And then because of that, it's going to be a polar molecule. In this case, the nitrogen has a negative charge. So bent, it's easy. All bent molecules are polar. Doesn't matter. Doesn't matter what it is. It can be ozone. Ozone is a bent molecule. It's all oxygens. Ozone's polar. So planar, for planar molecules, if you have the same, if you have the same atom on each side and or they cancel, I can show you some pictures later, but if all the atoms are the same on each side, then the whole molecule is nonpolar. So you can see the very, very symmetrical molecules are nonpolar. And then the planar molecules, or sorry, this one here, when you have a break in the symmetry, So where you have, so formaldehyde here, we have an oxygen instead of a hydrogen. So you have a different atom. Therefore, this molecule is polar. So you're getting that so far for linear. If you have everything the same, it's nonpolar. If you have one thing different, it's polar. For planar, if all the same, it's polar. I'm sorry, if all the same, it's nonpolar. If one atom is different, it's polar. Same thing with tetrahedral. So tetrahedral, if everything is the same, so if you see here with methane, all atoms are the same, it's nonpolar. So then what if we start playing some game where we start changing the atom? So, okay, you can see this. So what if I replace an atom of hydrogen with chlorine? So I have, so chloromethane. What is this molecule? Is this polar or nonpolar?
Polar.
This one's polar, right? One's different. What if I put a chlorine here? This molecule polar or nonpolar?
Non-polar.
Nope, it's still polar. So remember the tetrahedron is like is like this. So you have two atoms like this. So this molecule, as written, is still polar. So remember, this is in 3D, not 2D.
Mhm.
So what if I add another atom there? I should change the color, sorry, to keep it consistent. What if I add another chlorine here? Is this polar or non-polar?
Polar.
Polar, correct. That one's chloroform, if you're wondering what the molecule is.
Great.
And how about now? Carbon tetrachloride,
Mm,
non-polar, yep. Everything's the same, it's non-polar.
No problem.
No problem. And why do we care? So what? Why do we care? Because polar things dissolve in other polar things, and non-polar things dissolve in other non-polar things. So water things that dissolve in water tend to be polar, and things that cannot dissolve in water tend to be non-polar. So oil is non-polar, doesn't dissolve in water. Vinegar, alcohol, both polar, they can dissolve in water. Vinegar and oil, not so much.
Because water is polar.
Yes, and oil is non-polar. So, and also pyramids, all pyramids are polar. That's another easy one. So any pyramid is polar, any bent molecule is polar. If it's planar, tetrahedral, or linear, if it's symmetric in terms of atoms, it's non-polar. If one's different, it's polar. That's basically the gist of it. And I think from that, I'm gonna start the activity. Did you Zoomers, I don't know, did you get you got the email I sent out, right?
Yeah, they printed it out.
Okay, so that's what we're gonna do. Actually, I'm gonna stop the recording.